So today we're gonna cover three topics. First one is, four elastic constants, Young's modulus, Poisson's ratio, and shear modulus and bulk modulus K. And as a second topic, we'll discuss about Saint Venant's principle. And third topic, we'll discuss about the topic on stress concentration in structure. So let's begin from the first topic, which is elastic constants. So I think even though you haven't taken ME231, you may already know the concept of Young's modulus, maybe from freshman physics or high school physics. So the concept of and definition of Young's modulus is following. Young is name of a person. Okay, so not it doesn't mean that like you are young. Like yeah, I mean it's named by somebody, some famous guy. So Young's modulus is defined by this kind of loading. So when you have axial loading, yeah, so you do make a like tension test along some specific directions, and there is no other constraint in like a side walls. Okay, as in this three-dimensional picture, you are only having like tension test in one direction. The other two direction, yeah, is leave as it is. Okay, and after tension, what you can expect is that originally this shape body will be elongated along the tension direction, but it will shrink inside the walls. Okay, so this is how you perform experiment to measure Young's modulus. Okay, so if I make it more mathematical expression, these kind of loading can be defined as the stress in y direction, stress in g direction is 0, but strain in y direction and g direction is not 0 because you don't have any constraint, and typically material shrinks in cross section under tension. And the relationship between stress and strain along the same direction and its proportionality constant is called Young's modulus. Okay, so you have to always remember that the experiments is performed following these conditions. Okay, so you leave your sidewall free, like a zero traction force, and you do perform the tension test along one direction or compression test along one direction, then you expect this kind of relationship. And this is what you're gonna expect under tension. Under compression, you're gonna expect that your sample will become like shorter but fatter, right? Yeah, so this is what you're gonna expect during the compression. Okay, so you can measure Young's modulus either tension or compression along one direction, and the other direction leaves without any stress. Okay, and because of that, the cross-sectional area changes. Now, having measured the Young's modulus, one have to define the Poisson ratio too. Okay, so Poisson ratio V is defined as lateral strain divided by axial strain. Okay, so lateral strain means strain along in that direction or that direction. Okay, so typically mathematically, because the sign of strain is opposite, when you make a tension in x direction, you're gonna have shrinkage in y direction, so that epsilon y will be negative value. So typically Poisson ratio, to make it positive value, you define this as minus epsilon y over epsilon x, or minus epsilon g over epsilon x. Okay, and if we write down epsilon y and epsilon z in terms of epsilon x, you can write down in this way: minus Poisson ratio epsilon x. And typically for metals, Poisson ratio is around 0.3, and for rubbers it's around 0.5. And the implication of Poisson ratio of 0.5, yeah, we're gonna discuss about this maybe in later chapters, but actually this means volume conservation. Yeah, so they shrink in this direction only to compensate the elongation in axial direction for rubbers, and nu equals 0.5 means volume conservation. And yeah, you can think about this why it is so. Okay, and And of course, for metals, this is for the elastic range. The metals in plastic range beyond the yield, yeah, metals also shows 0.5 Poisson ratio. Okay, so this is interesting knowledge about materials. But maybe in our lectures, we're not gonna get into the deep into the materials. So just to remember, yeah, there is a material property called Young's modulus. There is material property called Poisson ratio, and what does it mean? That would be enough. Yeah. Yeah, regarding the physics of material response, yeah, you're gonna refer to more advanced classes in next years or in graduate schools. So having defined Young's modulus and Poisson ratio, and uh, if you also recall the superposition principle, we can make a generalized Hooke's law. Yeah, what is Hooke's law? Yeah, Hooke's law is F equal kx in freshman physics, or for simple axial loading, you can write down a stress strain version in this way: sigma equals to be E times x. E is Young's modulus. No, E times epsilon, right? So now generalized Hooke's law says that you in addition to sigma x, you have non-zero sigma y, non-zero sigma z, and what will be the displacement of this guy. Okay, so to obtain this, yeah, if you look at this problem, it looks quite complex, but please record that for linear response problem, you can decompose the forces into several parts, and after obtaining the response of each problem and summing up the response, then you can obtain the response of original problem if the sum of the forces from decomposed problem is same as original problem. So one simplest way is you decompose this three stress into first problem and second problem and third problem. Okay, yeah. So regarding the just axial loading along x direction, epsilon x must be sigma x, and epsilon y and epsilon g must be minus nu epsilon x, and epsilon x is given as sigma x over e. So you can write down in this way for response for y direction and z direction. Regarding sigma y, then you have epsilon y in same form with this guy. Then the other direction, x and z direction, yeah, you have minus nu epsilon y over e as a response. And for g directional normal stress sigma z, you have epsilon g in this way, and the other two seems has like a minus nu sigma z over e as their x and y strain. Okay, now if you sum up strain for x direction and strain for y direction, strain for z direction, then you're gonna obtain this final formula based on superposition principle. Okay, so this is how superposition principle is useful, and you're gonna rely on superposition principle a lot. Okay, so this is generalized Hooke's law under general normal stress sigma x, sigma y, and sigma z, and this connects the complex stress state with complex strain, the strain of the material. So having defined the Young's modulus and Poisson ratio and try to obtain generalized Hooke's law under general normal stress, okay, and massage the equation based on superposition principle, let's move on to the definition of another material property called bulk modulus. Yeah, I think some of you and most of you may heard about bulk modulus in freshman physics, right? I remember when I was first year, there was a section on like a sound propagation in freshman physics, and somehow the textbook make a really rough definition about bulk modulus and discuss about how sound propagates, right? Maybe some advanced high school physics book may have the definition of bulk modulus, but anyway, bulk modulus mathematically characterize the response under hydrostatic loading. And what I mean by hydrostatic loading is when sigma x, sigma y, and sigma z are equal to each other. Okay, then bulk modulus K is defined as this, and P is the pressure, and delta V over V is a change in volume and the original volume, and you put negative sign. Yeah, the reason is following. So when you have originally this big sample, and under hydrostatic compression, what you can expect is the sample will shrink. Okay, so the change in volume will be negative number. Okay, so change in volume in negative number, and you use like a ratio delta V over V because you want to make a material property independent of size, because even though you are applying same pressure 1 atm, whether you consider like this big sample, whether you consider this big sample, or whether you consider that sample, your absolute value of delta T will be different. However, if you consider the ratio delta V over original volume V, whether you consider small sample or intermediate sample or large sample, yeah, this ratio will be same for same pressure. That's why you have this ratio. The reason why you put a negative sign here is because delta V is typically negative when P is positive, and P is negative when the material is under tension. Then delta V will be positive. Okay, so that by doing this definition, you can make your bulk modulus as positive value. Okay, so typically it's convenient to leave material property as positive number, and that's why they put this negative sign here. But you gotta be careful about the sign convention. So in freshman physics, this little p is or pressure is larger than 0 if it's compression. However, in Me231, when you consider sign convention of stress, stress is positive when it's under tension. Okay, so please do not get confused too much about this. When you see like a stress, you typically see that most textbooks say that positive stress is tension. When somebody refers to pressure, most textbook considers positive pressure as sort of compression. Okay, so this is the distinction you have to remember for solid mechanics area. Okay. So now let's keep move on. So based on generalized Hooke's law, yeah, we can make a relationship between bulk modulus and Young's modulus and Poisson ratio, like using the generalized Hooke's law, and let's do that. So when you have this kind of loading, sigma x, sigma y, and sigma g, as I told you, because of the opposite sign convention, we can say that minus pressure equals to b, sigma x equals to b, sigma y equals to b, sigma g, because we are considering hydrostatic loading, and hydrostatic loading means that sigma x, sigma y, and sigma g are equal to each other. And let's consider the relative volume change, delta V over V, and yeah, our textbook says this is E, but different textbook use different alphabet for delta V over V. But anyway, so you can obtain V prime minus V divided by V. Yeah, this is change in volume. And how you can obtain B prime? Yeah, B prime is simply 1 plus epsilon x multiplied by 1 plus epsilon y multiplied by 1 plus epsilon 0. Yeah, I put, yeah, this original length is 1, but if original length is not 1, you instead of 1 you just plug in L. Okay, so after plug in these relationship, what you're gonna do, what you can obtain is after plug in this and get rid of second order term, like if you ignore these terms, because typically we are considering very small strain for our solid mechanics class. Okay, so after ignoring all those second order term or third order term, yeah, you end up with epsilon x plus epsilon y plus epsilon g as the ratio delta v over v. Then how we can obtain epsilon x, epsilon y, and epsilon g? Yeah, we can obtain that from generalized Hooke's law. Yeah, now the fortunately we have same sigma x, sigma y, and sigma g. So after we plug in like a different sigma x, sigma y, and sigma g, this is what you're gonna get regarding the summation of 3 normal strain. And as I defined in the beginning because we are considering hydrostatic loading. Yeah, so all of them are same as negative p. So it can be written as 1 minus 2 nu over E multiplied by minus 3p. Now let's plug that into our definition of the bulk modulus. So what we do is we leave this p in the left hand side and put all the other terms to the right hand side. So you leave delta v over v. So what you can realize is that you can identify the expression within this dotted square as the bulk modulus. Or you can say that bulk modulus can be written as Young's modulus divided by 3 times 1 minus 2 nu. Okay, so this is the relationship between Young's modulus, Poisson ratio, and bulk modulus. And from here, what we can realize is if somebody tells us 2 out of these 3 elastic constant, yeah, then you can obtain the other one, using this relationship. Okay, or in other words, out of these 3 elastic constant, Young's modulus, Poisson ratio, and bulk modulus, only 2 are independent. Okay, and other implication here is to have k is larger than 0, we need Poisson ratio smaller than 1 over 2. Yeah, this is very important, and positive k has some physical meaning. Okay, yeah, so when you have a material, and consider that under compression, yeah, here, yeah, because it's under compression, pressure is larger than 0. Okay, what you can expect is, yeah, under compression, yeah, material will shrink. You're gonna have delta v is smaller than 0. Okay, yeah, this is the typical material response, and because delta v is smaller than 0, yeah, what you can expect is that you are trying to shrink the material, and material wants to expands back. Okay, so this is typical response for k is larger than 0 material. However, if you have a material with k less than 0, you're gonna expect something really weird. Okay, so the weirdest thing is when you have some material, whose original size is like this. Okay, and if you try to make a compression, what negative k means is that p is larger than 0 and k is negative value, and this is negative sign. What you can expect is volume will increase. Okay, so under compression and volume will increase, and under tension, volume will shrink. Okay, so it's of course unstable material, and we cannot have this kind of material in real world. Okay, and that's why k must be larger than 0, and that's why Poisson ratio is equal to or smaller than 1 over 2 or 0.5. Okay, so when somebody asks you what's the typical range of the Poisson ratio, your answer must be Poisson ratio must be smaller than or equal to 0.5 or 1 over 2. Okay, so that's the lesson I want to give regarding the Young's modulus, Poisson ratio, and bulk modulus. And we still have one more elastic constant, and I'm gonna discuss about that last elastic constant, which is shear modulus, in the next video.